Okay. So we're talking about today partially composite insulated wall panel testing program that we did with the Tilted Concrete Institute. Excuse me, the Tilted Concrete Association, TCA. It was really a team effort. We had myself, grad students, Salam and Zach. Steve Myers is our contractor from Tilted Concrete Incorporated in Lincoln, Nebraska. He's kind of amazing. We also have steering committee overseeing this work. Jeff Needham, Joe Steinbecker, and Phil Hope. Mitch Lundquist and Craig Coppersmith provided oversight on this project. And so this is a very large industry-driven effort, right? This is not really very academic. We had connector suppliers that you see below, Dayton Superior, HK Composites, Icon X USA, Instruct, and Thermomass participate in this work. So the presentation I'm gonna give you today is way too big for 30 minutes. I can't possibly cover all this stuff. And we've got a 300-page report coming out soon. Was that 10 pages a minute? You're going to get the high level stuff here. It's just too much. I'm happy to come back and give my presentations. So we're going to talk about the background experimental program and the proposed methods. Again, not really in detail. We don't have the time, but really the high level, just to really understand the behavior of what we observed. Because there's tilt-up panels are being built, but it's still, excuse me, tilt-up composite panels are being built, but they are not routine yet, and we don't have design provisions for them. So anybody that's not familiar, insulated walls are typically a 3-layer wall. So it's concrete, insulation, concrete. Those layers of insulation are then connected using some kind of connector, whether it's a steel connector, GFRP, CFRP, whatever that is, so that we can penetrate that insulation to provide some composite action. There are non-composite panels as well that just don't transfer the shear between the layers. But these are highly structurally efficient, and the whole reason we're doing this is thermal efficiency, right? But additionally, there's a lot, especially in the tilt-up world, a lot of motivation for reducing weight of panels. And so just simply putting that insulation in there, reducing the weight of panel is very attractive. So one of the big reasons we do this, right, is to save the environment that we want, or really, cost us less money when we pay our electrical bills. And so we want good thermal efficiency. But we also have to meet building code requirements or energy code requirements, and really insulated wall panels really help us do that kind of thing. So very briefly, let's talk about the differences between a non-composite panel, a fully composite panel, and the partially composite panel. Now, I don't believe anything actually exists except for a partially composite panel. Everything lies on some kind of a continuum, just like everything else in the world. But a non-composite panel typically assumes that 2 layers of concrete are going to act independently. Okay, a fully composite panel assumes that they're going to act completely together. That is not achievable unless you have longitudinal concrete ribs and/or lots of solid zones for lifting hardware or around jams or whatever that is. Partially composite panels live in the middle of that, where we're not able to transfer all of that force, and so we behave somewhere in the middle. This is, from an engineering standpoint, very challenging, right? Mostly because there's no code provisions, right? So, did you take a class at WashU on sandwich theory? I didn't think so. I mean, oh yeah, sure. I'm gonna start a sandwich shop called Sandwich Theory. Yeah. But anyway, these are skills that we don't have, okay? Especially not within the code. So because there's no recommendations that exist, And there's not really any public database on insulated wall panels. There's tests out there, but like I said, we partnered up with the manufacturers. A lot of that is, trade secret type information. And so that information is not out there for us engineers to be designed with. There are panels in the literature. Most of them tend to be, research scale stuff, like 10-foot long. I mean, when's the last time anybody designed a 10-foot tall wall? Not very often, right? So one of the big motivations was, can we do this at scale? Can we do this in 40-foot plus panels? 41 in this case. So our goals were to obtain information on panels with a variety of connectors, predict composite panel deformations and second order effects, and also be able to predict when the connectors are going to fail. Okay. I mean, those are the things you as the engineer are going to need to make sure that panel doesn't cause problems. So we want to provide engineers and contractors this information specifically so we can understand the nature of composite panel design. And one of the big challenges is the industry has previously been very kind of black box. Every connector manufacturer does things a little bit differently. They will help you design a panel, but ultimately the engineer has to stamp that panel, and they're not going to stamp it for you. And so understanding all aspects of this panel, or this panel design is very important. So we want to bring it to the point where you buy a piece of rebar, right? You put it in a panel, you understand what's going to happen with that piece of rebar. That rebar has been tested, it's been pull tested, every heat, all that stuff. So you can take that, be very confident, put it in the panel. You want to get to the point where you can relate the insulated wall panel connectors to all aspects of insulated wall panel design. Right? Straightforward. That's what we as engineers would like. So these are the connectors that participated in the study. On the left, you can see that's the superior delta tie. The next with an icon X, model 23. The next is the HK CA tie. The blue one there is MMS CC. Thank you. And the last one is an EBG or in-strut galvanized wire truss. Okay, so that's pre-installed in insulation. I don't think I got a good picture of it, but it's two grids. You see the X's, those are weld points. It's two welded wire grids, and they weld those cross wires going vertically in this picture to each other. So the panels we designed, they were all 4 foot wide. You can see we tested solid panels that were 8 inches thick with 2 layers of reinforcement in each case. The insulated wall panel had a similar configuration, except we took that 8 inches of concrete, split it down the middle with 2 inches of insulation. And then we told the connector suppliers to design this for some loads that we gave them, situations that we gave them, and off we went. For testing purposes, I know you don't do this in real life, right? We've got bull nose details at the bottom of the solid panel, a single bull nose. At the top, we needed a double bull nose because we're applying 2 point loads to it. The reason we had to do that is because of the way the sandwich panel was configured. So we had a double bull nose on the top and bottom of the insulated wall panel. And I think you'll see the way the rocker arms worked in our setup. We had to do it that way. So Steve Myers, Tilted Concrete Incorporated, did all the construction for us. We did a really great job. These guys are incredibly efficient. Steve's a great contractor. Here you can see all the different types of panels being created, all the different connectors. I think we've got HK here, delta tie there, thermomass there, and EBG there. Oh no, and those are icons up in the middle. So all of them are represented, so nobody can find it. And one thing Nebraska has is beautiful sunsets. We tested in the cold, in the heat. It was pretty horrible, but we did it. Oh, let me go back. I'm sorry, went too fast. So here you can see our test setup. So this thing, I think you can see. Oh, you can't see that. You can't see this very well. So our panel length is 41 feet long. We tested on edge, not vertically. You saw in the previous presentations that testing was done vertically. 41 feet in the air is pretty high. It doesn't look like it's that long, but it's super long, super scary. What we did is we set this up outside, of course, on two supports. You can see them here, on PTFE sliders. We got an airbag behind it, which I'll show you here in a second. And if we got two guys to lean on that, it's like pretty slippery. We greased the PTFE as well. And just barely, you can see this. That's our rocker, our assembly, which I'll get a better picture here in a second. So along the length of this panel, we had 12 different deflection measurements. It's very, very critical because the way we set the panel in to have extra deflection measurements at the end. So each one of those squares represents a wire potentiometer to measure deflections. And so whenever I report the midspan deflection, I'm actually reporting the difference between the two, the average of the four at each end minus the middle, right? So that we don't have any support interaction with those measurements. Next, we wanted to measure the inner white displacement. We wanted to know how is the shear occurring along the span. And here's the rocker arm. So as you can see, the dimensions aren't on it. It's a 10-to-1 amplification. So we had right here, that's the center pivot of this lever arm. We had an anvil down here, and at the top, we measured the load, and you'll see it on the slide. Here we go. We got load cells, tension load cells at the top. They're not actually set up right now. They're close. They're almost set. But you can see they're reacting along that bull nose at the bottom of the panel. It's kind of dark right there. And then Zach's. But so they're set. It was not an automated procedure. You can see there's three guys there trying to get that aligned just right. But our goal is to apply this load right at the top of the panel, simulate half the panel weight, and also an eccentrically applied 5,000 pound force. Those are the hanging concrete weights. You can see we put extra beams on there to get just the right weight. Those are not hanging right now, but they came over the top of those A-frames on a pulley. Our airbag was 40 feet long. It's actually 4 different airbags. You can see there's multiple hoses coming off the top of that wall. Every time we would fully inflate it, it would inflate 30 inches. Every single panel, we push 30 inches. It's pretty spectacular. All right, and the final thing we did, and this is probably the most important, is we wanted to do a double shear test. So this is a double shear test that's been done on insulated wall panel connectors for maybe the last 20 years or more. But we had, this is not supposed to simulate a panel. This is not a panel, even though it looks kind of like a panel. It's 5 layers, right? We've got concrete, insulation, concrete. The goal is to set this panel or this specimen in a situation where we can apply shear to that connector, measure the deformation, and then plot the load and deformation versus each other to get kind of characteristic behavior, almost like a stress strain curve. Okay? So this is what it looks like. You can see this panel here. We've got something like 3 inches of deformation because it used to be flush at the bottom. Learn that better.
There it is. There it is.
There we go.
Time what?
All right. So I'm going to start off with this data just to show you how different each one of these different connectors are. This is the connector A, and connector A almost looks like elastic, perfectly plastic. We've got on the y-axis, we've got load. On the x-axis, we have deformation. Okay, so we load that up. If we look on the left, that's just a zoomed out view. On the right, we've got a zoomed in view. Right, so remember this slip is that inter-wife displacement. So you can see it's exceptionally stiff, hits a point, and it goes. And it's almost perfectly plastic after that point. I think it's super cool, very ductile. But at the same time, it's exceptionally stiff. You can see it peaks at about 0.05 inches. Pretty cool.
Say that one more time. One direction and another direction.
Once it hits its load, its early load up here. I don't know if you can see my pointer. Once it hits its early load, right about here, it just goes off to the side.
Right.
No additional load, large amount of it displacement. Carries that.
That's another direction.
No. That box
Oh.
it's a zoomed in view of that. Yes.
Sorry.
Doesn't like these slides or something. Oh, connector B, kind of similar. It peaked at a similar shear deformation, but it did not carry load continuously after it hit peak. It dropped down, I would say fairly slowly, but it eventually did, it dropped down rapidly. Compared to this one, or not that, compared to the previous one. Can't make this thing work. All right, so this one's very great. I think it's the data. I don't think it's this. Okay. This connector, they hit almost linearly. I can see it's a little right? They hit almost linearly up till failure. And then there was nothing afterward. There was no post-peak deformation. Yeah, I think it's the data. That almost looks like I did a pull test of a rebar, right? That's the classic thing. When I teach steel design, I've got the elastic region, the yielding region, and the strain hardening region for a piece of rebar. This connector is not rebar. This is glass fiber polymer. Very cool. But you can see that in the early range, it does have that plateau effect, and this does gain some strength. And this is glass fiber polymer, and it goes all the way out to 1 inch. Right? We normally think of glass fiber polymer rebar as it's not rebar. Glass fiber polymer is very brittle. That is true, but not this stuff. Not the way we're loaded with stuff. All right, next one. This one was very stiff, but it did have a downslope. It's kind of interesting. But very, very similar to B, maybe a little bit stronger and a little stiffer. So what you can see is we have to deal with all these different types of connectors. They're all very diverse. They have different strengths, weaknesses, stiffnesses, all that fun stuff. So here you can see a little time-lapse video of us testing a panel. Each panel took us about an hour to test. It shouldn't sound that long, but it took us 3 or 4 to set each one up in the cold. Not fun. It's the most physically painful project I've ever been a part of. We did it in the summer too, and all of our hardware kept shutting off because it's too dang hot. We all prefer the winter, actually. It was horrible, but way better. Anyway, so we're talking about slender wall provisions. You can see on this plot, you're going to see similar plots just like this, but we've got this dash line, black dash line here. You can't see it because it tracks that early gross stiffness very, very well. Hits this point, we use 2/3 MCR and MCrack up there. The end of that dash line, that is slender wall. You can see it tracks that data exceptionally well. We tested 3 solid panels. I labeled them 4, 5, 6. We actually tested 3 more, 1, 2, 3. which is not here. Also, you'll see the gray line response 2000. That's a moment curvature deflection program that's fairly well vetted. It tracks the data even better. It actually takes into account some additional tension stiffening, which is critical to predicting deflections of concrete elements. But it does even better with Slender wall. So here's a panel, solid panel. You can see very well distributed cracking. You can see those sliders kind of moving around here. This is at about 30 inches of deflection. We had cameras all over the place. This is one of the better shots. You see, by the time we ended up doing the testing, the panels just blind. We were lousy with them. They were all over the place. We tested like 25. We didn't have enough space to put them. You can see them stacked all over the place. All right, so this is the 8 panels here. This is an insulated wall, 4-inch insulation. That looks like a solid wall to me. Right, this thing comes up just like Slender wall, goes up, cracks, same slopes, same everything, kind of cool. This one does have solid zones of concrete in it, but it is an insulated wall. So if you've got very large solid zones, some of the provisions that the methods that we're going to talk about may or may not apply because they don't really behave like an insulated wall. It's very much a solid wall because there is some characteristic behavior we're going to see in just a second. But here's another panel. This is that A series panel pre-test on the left. On the right, you can see that, remember, we had welded wire mesh, right? So welded wire ruptured at that point. Right there, you can see this cracked concrete here. Here you can see we tried to break off as much of the concrete on the edges as we could, but it was kind of tough on that one. We ended up with some solid zones around that panel, specifically the lifters, right? The burnout insulation, just so we could lift the thing. Next up was connector B. Connector B had slightly different behavior. That last one ended up with a FLEXURAL failure. This one ended up with a connector failure. This was intentional and was in no way an indictment on connector B itself. We intentionally removed connectors to do this. But here you see, if you follow the Slender wall provision, you're not going to capture the behavior, right? In two places. Here, where cracking occurs, insulated walls crack earlier and deform more in the elastic range and then everywhere else than solid walls of the same thickness. Also, you're going to see this rollover behavior. See how it kind of rolls? It's going to crack down here, this range, and going to start rolling. This one didn't have a chance to finish what it was going to do, which we'll see on the next panel, but we had that rollover behavior, and then the connectors couldn't hang on any longer. They went pop, 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 and it was done. You can see the average ultimate moment was 45 kips. Compare it to the ultimate moment of a solid panel with the same thickness. It's way below that. And also, you're going to see this. This is going to stay on most of the slides here. Cracking moment was considerably less. Right? The more connectors you put in, the more cracking moment you'll get, but it's impossible actually to get a fully composite panel of cracking.
Quick question, just to clarify. When you say solid panel, so if you've got a 3-3-3, you're comparing your 6 inches of solid concrete to 9 inches, right?
So this panel was a 4-2-4. Okay. And when I say solid, the equivalent solid, I'm talking about a 10-inch total thickness panel. So that full thickness. That's what this. Even though we tested an 8-inch, that's not this is a 10-inch.
We have the same amount of concrete as an 8-inch panel. We're getting more strength than an 8-inch panel. We're also sometimes getting close to the 10-inch panel.
You'll see on this slide, you can absolutely achieve the strength of a 10-inch panel. So this is connector C, highly ductile connector. We actually tested 4 of these instead of triple kit we did. First thing we did is we tested C123. C123 all had the same reinforcement. C4, we said, we want to see it fail in shear. Right? We wanted every connector to fail in shear. I think that's a very important thing to prevent horizontal shear failure. We begged and pleaded and said, can you please remove connectors, even though you would not recommend us do that. And so C4 is this little dashed one here, kind of comes off to the side, down below the others. Okay. You can see we have that characteristic rollover behavior. We have cracking in this range here. We have this characteristic rollover behavior, and then it stabilizes and it achieves the fully composite strength. Very, very cool. Put connectors out for C4 with the intention of creating that shear failure. We still got very good ductility. You see that it is less stiff than the others. Our data was very tight, and especially post-cracking. These two, see, they don't come super close. Excuse me, not to this black one was pre-cracked. Several of our panels couldn't make it all the way through storage to get tested in the pre-cracked state. Anyway, very, very cool. D, very similar. We tested that fourth one, C4, or excuse me, D4. We removed, I think, over half the connectors. Like, I'm not talking about when you saw it, we removed a huge number of connectors. You can see almost double the deformation of failure because of that. That's shear deformations. Our shear deformations are very, very large. That's how large. That is a lot of edge-of-white slip. That is post-test. But that's it. You can see the insulation. We debonded the insulation on purpose. We didn't want any bond affecting it, so we used 2 layers, 1-inch insulation instead of 1 layer of 2-inch. That express purpose. All right, E panel, very similar to D panel. Excuse me, B panel. I know the names, there's not stuff to tell you. But we have shear failure. Again, this one was a little bit stronger than the others, but again, this is intentional. We start that rollover behavior, the connectors have enough, and then they start going. There we go. Here you can see what happened when this particular connector failed. The layers actually separated both horizontally and vertically. It's just because of the way that connector kind of behaved. It kind of moved up over itself. So you can very easily see that movement. See that line, this line was straight to begin with, and that insulation was perfectly lined up. All right, so the testing was super cool. Lots of really cool information that no one's really ever gotten before. But engineers need more than just some cool data, right? We need some analysis methods to create second order deformations, and we need to be able to prevent connector failure. So one of the coolest things that we observed, and I'm not saying we're the first to observe this, but we found most panels, if they were if they didn't experience connector failure, had 3 very distinct regions. You can see them here. You have the uncracked region. We have the region where just one white is cracked, the other white remains uncracked. And then we have the region where both whites are now cracked. Okay, so using this, we were able to kind of jimmy rig an elastic method that could predict the full curve. And it did a pretty darn good job. It was super sensitive to design selections like tension stiffening models. Where we pick cracking, 5, 7, whatever you pick, right? But we call them, I'm not very creative with names, so I call it K1, 2, 3. Right? So it's the stiffness is K for each of those 3 regions. I'll come up with a better one later, maybe. But you can see if we did this method for E1, see it almost follows that data almost perfectly. D4 was kind of the star of all the panels we tested because remember all the force D4 and D4 they were intentionally shear failed huge deformations near the anchors. If we did slender wall on the E, you can almost say that might work. Right, so dash line, black dash line, slender wall. You can almost say that you might be able to do that. So, Maguire, why are we worried about it? Right? I mean, we can just use that. That's why you can't use slender wall, because that thing deflected twice as much as slender wall. That's super bad news, right? So K123 is able to capture that full behavior all the way up to failure, which is very, very neat. Now, I'm not going to get into K123 too much, just so that we can, I really don't put it in there so we can describe this three region behavior. That's kind of a critical concept. What we need is a design method that fits with an existing workflow. And so we came up with what's called slender wall method for sound 12 panels, otherwise known as modified slender wall. Okay. So slender wall method is the black line. Modified slender wall, all we do is we have to do some kind of sandwich theory. Sorry. To predict this second, or this first point. We have to modify that cracking rule. Every insulated wall panel is going to crack at a lower stress because of the way these panels deform. It will also deform more. There's lots of different ways to do that. Connector suppliers have been doing it for years. Most of the time keeping it in the elastic range. So this is almost the easy part. Okay. I've got multiple methods out there to do it. You can do beam and spring, matrix analysis methods. It's very straightforward. I'll give a presentation on that later. But this is the part that we've never really gotten until now, right? So at this ultimate strength level, how do we predict that shear deformation? And I think we came up with something that was relatively simple, that equation. So delta is deflection, CR is for cracking, and then PC is partially composite, and FC is fully composite. So this point here, this cracking load, those two cracking loads, the difference between the deflection at those 2 points, that's shear deformation. That's the elastic shear deformation. Okay, so what we're going to do is we're going to take that elastic shear deformation, and we're going to determine from one of those other analysis methods what the slip is, what the inner white slip is for those connectors. And we're going to extrapolate it out to the ultimate deformation of that connector. So we end up with a relatively simple equation. We're basically just extrapolating, ratioing this early deformation stuff that using information that if connector suppliers are already determining, we can now do it too. But the challenge with this method is it is a bilinear method. It's not a trilinear method. It also completely ignores tension stiffening. So remember, in the K123 method, the whole point was we had these three different regions. The K2 and 3 regions are basically tension stiffening on steroids. But once that tension wife cracks, those connectors really get engaged. They compress that compression wife a lot, delaying cracking considerably. Right, so you basically, you don't have one member anymore, you've got two members. One squishing the other one, basically, the way it's working. So we cannot get that rollover. See, we missed the rollover, but we do that intentionally with the goal of being close at the end, just like Slender Wall is basically trying to do the cracked portion. So again, D4 and C4 were the most critical. They have considerably more deformations than the other panels because we basically force nearly a combined flexural and shear failure at the same time. It's kind of a worst case scenario for this behavior. All right. I don't know, I'm probably over time, but can we predict shear failure? Over here on the right, you see these three dots correspond to these three curves. Shear failure occurs when we do a double shear test, or when the inner white slip reaches the maximum slip from the double shear. And we've seen this. And this plot is the slip along the length of the panel plotted a point along that length of it. So what we came up with is something that looks like this. We assume it's linear. If you look at this plot back here, that's not linear, right? We want to approximate it. But what I recommend is a linear approximation. If we assume this, we assume that interconnector fails. And we just set it at the maximum strength or whatever point we want to use to design. We say then, once that's true, and it's linear all the way along the length, we can then look up on the double shear test data each point, simply add them up. So that first equation is our linear slip approximation. Over on the right, we're just setting the slip at the max load. Predict our horizontal shear, adding up all the forces interconnected based on that. And pretty straightforward. And it does a decent job. Here you can see two different methods, a linear method and a bilinear method. The bilinear method does an even better job, it's less conservative, but that linear method is what I just described. It does a pretty decent job of predicting when these shear failures are. These are all the panels that experience shear failure. None of these experience flexural failure. All right, running out of time. But we tested 17 insulated and 6 solid panels. We wanted to see different failure modes, and we had different design conditions. Panels B1 through 3, E1 through 3, C4, and D4 exhibited connector failure. A1 through 3, C1 through 3, and D1 through 3 all had steel yielding. Panel deformations and failure were well predicted by the new methods for tilt-up composite walls. We've got 2 different methods for deflections and moments. And we've got 2 different methods available to predict connector failure. One thing, since we're running out of time, I won't talk much about shear flow, but if you want to talk about this last bullet and why it does not consider shear flow, I'm happy to talk about it.
Come to convention.
Yeah, that's right. Thank you.